Anybody else need one? Great. I've been dying to put up this statistic since I compiled it this afternoon. So a perfect score was like a 30, but if you did the math, it was actually like a 32. So there was embedded in the problems were a little bit of extra credit points. And so greater than or equal to 30. 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, 6 people. That's outstanding. That is outstanding. And it's a testimony to the fact that this exam is a very doable exam if you keep your wits about you. Like the last problem was one where you just had to keep your wits about you and answer the big long AM problem. Again, just have the confidence and crank through it. So that's great. But it doesn't end there. 25 to 29. 1, 2, 3, 4, 5. 1, 2, 3, 8 of you guys. Perfectly respectable 20 to 24. 1, 2, 3, 4, 5, 6. 15 to 19. 1, 2, 3, 4. 10 to 14. 1, 2, 3, 4. And then less than 10, 5 of you. Now, a couple of other things. 20 out of 33 got a 7 or 8 on the homework problem. Okay? So 2/3 of you guys nailed the homework problem, which is exactly how it should be, except that this number should be bigger. Right? I really do, And also think about the homework problem. It was, we had studied the Hilbert transform. I didn't come up with a new problem on the Hilbert transform. But again, that was, I assume that you at least do the Hilbert transform to do the homework. Okay, and then the other thing that I noticed, there were 14 of you, and I don't know how to describe this, that had high positive changes. So I'm not talking. There were many more of you that went up by a couple of points, but half the class. There were 33 tests that I graded. Almost half the class jumped up by, let's say, 7 points or greater, which again is outstanding. And it shows that you guys are sticking in there and working hard, learn from mistakes. I don't think this was an easy test. Don't get me wrong. I don't think this was harder or easier than anything else I give you. I think you guys are just on it and doing well. And so this doesn't usually happen. There's 2 possible explanations. One is that we've moved away from signals and systems, the meat of it, and we're now doing applications. The other one, I think, is just you guys are, have learned from, are more used to the material and the presentation and so on. So I'm actually really happy with those statistics, and I just wanted to basically put those up there to congratulate you guys. Yes.
Well, thank you, Raj.
Yeah, congratulations. Sure. Anybody else do the exam? All right. Are there any questions on the exam? Okay. The first one is you can get from the homework. The second one. Well, I think you just work through it again carefully. That's probably a good one. Then the last one, I think most of the problems there were just about reading it carefully, and just working through it and knowing that stuff. So, all right. Where are we? Okay. We're almost done with pulse code modulation. Oh, good. All right. Yeah, let's have some fun here. So, because we've kind of slept since the last time I lectured last week, we're looking at pulse code modulation. There were basically 3 steps to the transmitter. There was sampling, there was quantizing, and we kind of did that. And we finished last time with quantizing. Remember the companding? Remember the little digression on standards? That's useful, I think. And then the last piece is encoding. To make sure our ones and zeros match well to the channel. So the channel is an analog transmission line, or free space, or glass. And because that's analog, the pulses that are ones and the pulses that are zeros need to be carefully shaped and tailored in order to be able to match into that. There's a whole bunch of other coding that will go on as well. But I want to focus. I want to focus pretty much on the physical picture of it. So, one thing to point out: there are lots of codes. And as always in comm systems, the choice is usually boiled down to some figure of merit, such as a bandwidth per cost. So the relative trade-off of the use of bandwidth versus the use of money. And so what I'm just going to do is I'm just going to describe some of the characteristics of these, and in a lot of ways you can mix and match. So, give you an idea. For example, so RZ versus NRZ. The RZ stands for return to zero, and the NRZ is non-return to zero. Okay. So supposing I have a code 0110, and I want to send these as little pulses down a transmission line. So what I'll do is I'll break this up into time slots. And what I'll do is when I see a 0, I won't send any pulse. And when I say a 1, I'm going to send a pulse. And if I'm going to send a return to 0, I'm going to rise. I'm going to send my pulse. And then I'm going to come back down to 0 before the end of that time slot. So now when I go to see my next pulse, I'm starting from 0. And I go back up, send a 1, and then come back down. Okay. For a non-return to 0, again, break it up into time slots. Nothing changes. Whoops. Nothing changes on the zeros. There's on the ones, we send a pulse, but in a non-return to 0, we're going to stay high for the entire piece of the time slot. We're now in the next time slot, and we have to send a pulse. We have no room to go back down, so we just continue emitting. And then on the next 0, that's when we make our transition back down to baseline. Which one of these uses more bandwidth? Which uses more bandwidth?
The first one. First one's higher.
So this is a shorter pulse. This is the time domain. Shorter pulse, so larger bandwidth. Which is more expensive? The RZ is more expensive? Why? Because it uses more bandwidth. Faster electronics, faster switches. Exactly right. Exactly right. Which is better? Cost aside. Well, you kind of think that because bandwidth costs money, and why would anybody do it? What are some of the reasons why we might think that RZ would be better? Yes, sir?
Rather than having to synchronize with your receiver, maybe, like in the second one. The first one, you just have to detect a pulse, and then you know you received a one. Whereas with the second one, if you're receiving that signal, you have to know how long that is and how many ones in a row that is.
Let me paraphrase it, and you can correct me if I didn't quite get it. I agree with what you're saying. If in this time slot, for example, it's unambiguous that you have a pulse there, and here you don't have that transition to really do it. So you can, within a time slot, you can compare a high value to a low value. Another piece is the way I've drawn it. I'm starting my pulse at the beginning of the time slot. Is that always going to happen? What's going to happen with the timing of this?
Skew.
There's going to be some skew. The word I would use is jitter. And so this would be less susceptible to jitter because it has some guard bands in the time domain. Okay. If I stream a long series of ones and a long series of zeros, which I can in fact adjust for, I can make sure that doesn't happen. But if I do that, then I often lose track of where my timing is. So I need a transition to reestablish my time slots. And these guys give me two transitions to do my jitter, to do my retiming upon detection. So it's a little bit. This is a little bit harder to work with on a receiving end, but it's certainly cheaper. Now, if you're using NRZ, then you can go back into your coding algorithm, and you can say, I want to shuffle in a known manner so that I know I'm going to have an equal number of ones and zeros. I'm going to try to ensure that. If I don't, I'm not using my bandwidth correctly. You can think about that. I want about a 50-50 mix of zeros and ones. If I send a lot of white space, I'm not really sending much information, am I? I need the change in a 1 and a 0 in order to actually send information. So if I just am quiet, I'm making a point, but I'm not conveying a lot of information, right? And so what you want to do is you want to scramble your ones and your zeros in a known manner, so that you mix it up. And that's one very. So if you're going to do NRZ, that's one very very nice way of doing it. It turns out that when you take into account a lot of the higher order processes, for example, in a real channel, a real link, you will always get better distance or better bandwidth usage for an RZ. In a fiber system, you can go maybe 50% further with an RZ versus an NRZ. And then that becomes an interesting technical trade-off. How much are you willing to pay for that extra distance, or conversely, the extra bandwidth? And can the electronics meet that value proposition? Okay. And what I've seen is that, you know, it depending on the price of electronics and depending on how things are, you know, there's an argument to be made going longer, souping it up, using the RZ, and there's also the argument cheap electronics and do NRZ. And so this is a real decision, right? And so I can't stand here and say always do RZ is always better, always do RZ, or NRZ is always better, always do NRZ. It's one of those things that it's a choice as a designer that you're going to enjoy making. Okay, and then I had to make it on the product that I was managing, and it was fun. Okay. Unipolar versus bipolar. This is not a psych class. So the polarity that I'm talking about here is minus voltage versus positive voltage. Okay. So for a 1, 0, 1, 0, I'm going to transition between a 0 and maybe A volts. Okay? Or A volts per meter, if that's an electric field. Or a 0 and A watts, if that's a light pulse. Probably 1 milliwatt. On the other hand, I could also send the same voltage by going between minus A over 2 and positive A over 2. And I'm going to write down this time volts. Okay? So this is unipolar. It swings from from off to on. And this is bipolar. It swings from minus to positive. Okay? Which one of these has a DC term? The unipolar has a DC term. If I'm sending an equal amount of ones and zeros, then the DC term is just going to be the average. A over 2? Is that right? I can do this with volts because we know where we can set our ground to be in the middle between a minus 1 volt and a positive 1 volt. But if I'm working with an optical signal, there's no such thing as negative light. There's only dark and light. And so I have to run unipolar. So again, this choice has, if you're able to make this choice, it has bandwidth implications as well. Now, if you think about your knowledge of electronics, just go back to your electronic circuits class. I know it's not required, but has everyone taken that?
It's required. That's required.
Is it a prerequisite for this?
No.
No, it's not a prereq for this. But it's useful to kind of think about in this context. If you switch a transistor you switch a transistor on an edge, right? And so if I look at the way we've been approaching RZ, NRZ, unipolar, we've said, okay, let's make a reading up here. But that's not the way electronics work. Electronics work on the transition between states. And so there's something called Manchester coding. That's expensive and not always possible, but I will always make a transition in Manchester coding on every time slot. I will always make a transition from either high to low or low to high. If I make it from high to low, that is, if I have a falling edge, that's going to be a 1. If I make it from a 0 to a 1, or a -1 to a +1, a rising edge will be a 0. So in a time slot, and this might be between -A/2 and A/2 for bipolar Manchester coding. Conversely, and then this is my time slot here. Conversely, if I go from there to there, that's going to be a 0. So if I want to send 1, 1, 0, draw my time slots. Going to start high, go down to low. Going to start high, go down to low, which means I have to come up. And then I'm going to start low and come up to high for my 0.
So I guess I was confused because, like, since you have to rise from the lower to the upper, that doesn't get seen as a 0 because you're reading the change within the time period, not at the start of the time period? Okay.
That's hard. I know, it's tricky, isn't it? And then what that means is you have to have really good timing.
Yeah.
You have to have really good timing, but you do because you've got a transition at this nice transition every center of the period. So you can do a count, and you'll always establish a very strong frequency component here, here, here. And what this is this will be a harmonic of that frequency component, and it would happen about half the number of times. So that harmonic would be about half the power. Okay, but in fact, the nature of Manchester coding means that you have very low jitter because you do always have an edge in the center of it, and that's why it works. And yes, that's the most expensive one of all. It's done with voltages of, So these are just some characteristics of codes. Some desirable properties of codes. Self-synchronization. And all this really means is we want edges. There are things called clock recovery circuits. If you're using a phase lock loop, even in a digital context, even a 1 to 0 context, it's going to want to see those edges. That's why Manchester coding is there. And even with RZ and NRZ, you want to scramble your codes so that you have lots of edges. So low probability of error, jitter, thresholding. We'll talk a little bit about that. But if your channel, sometimes your channel will suggest one over the other as being a lower error. In fact, in just a few moments today, probably, we'll begin down this path of sitting at the receiver, thinking about what the transmission line has done to our poor, nice little 1s and 0 pulses, and try to imagine ourselves figuring out, is it a 1 or is it a 0? And what that means. Okay? Matching to the channel. We want to have a suitable spectrum for the channel. And what can happen, so remember a transmission line has lumped capacitances and inductances. It also will have some parasitic resistances in it. And those guys are going to tune around with temperature and not necessarily uniformly. So what you're going to have is you're going to have resonant structures that you're going to try to fit your bandwidth into. There's going to be certain frequency slots that are going to go further in this transmission line than others. And so one of the things you can do, and what is done in DSP, is you interrogate your transmission line between the central office and your place of business or your house. And as that changes, you readjust the coding so that you can maximize your utility on that transmission line. So if that transmission line has a null in frequency that's going to reject any power at that frequency, you rejigger your pulse trains and your pulse shapes to avoid that null. And as that null shifts around with temperature or time, you redo it. If someone plugs in another jack, another lead into a jack, and loads down your transmission line boundary conditions, again, you may have to rejigger. Yes, sir?
I was going to ask, so you're sending like a reference signal and then calibrating?
So your modem does a lot of this. You think about how dead your modem is, right? There's plenty of times, coming down you might be streaming a Netflix movie, but going up you have very, very sparse data. And regardless, you're probably receiving packets and still have some dead time. Or at the end of the movie, for example, before you click on your next episode of whatever you're binging on that weekend, you have some handshaking time that can be used to retest the line. Okay, and the kind of development of that came out of a nice example of digital signal processing at a time when DSP chips were really, really being pushed. And what was great about that is a couple engineers were able to demonstrate that with just a couple of computers in their garage. And that formed Linksys. So, big ideas, big companies can come from a change in technology, a change in capabilities, a change in realizing your coding, and always be on the lookout for that. It's happening at the very top edge of the optical comm system now. We're moving to 400 gigabits per second and 1 terabit gigabits per second on one laser to one detector, and so for the first time, all the coding tricks. 16 levels of quadrature amplitude modulation, for example, are coming out, requiring tremendous amount of work on the transmitter end and even more work on the signal processing on the receiving end. And the circuitry that does that is startling. 16 QAM, which is used a lot in wireless at much, much lower frequencies, are now being implemented at 197 terahertz, which are the optical frequencies of the lasers that power the backbone. Yes, sir.
I don't know. I remember doing some sort of like abstract assignment for a devices class that was talking about like the future of computing being in photonics.
Oh.
I don't know what that. How
So,
that relates to this kind of thing.
Yeah, so you know, has any of you enjoyed a class with? Well, has any of you taken a class with Bill Frensley? He's a incredible. Have you? I hope you enjoyed it. He's a really bright person, really interesting guy. And what he'll say is, fermions are really good for processing, and bosons are really good for transmitting. And electrons are fermions, and so it's really, they're easy to, they're hard to move around, but they'll stay in one place to register a state of an on state or an off state. On the other hand, bosons, which are photons, which is light, they just want to move. Try to get them to turn a corner gracefully, and that's difficult. They don't want to do that. They just want to move at a foot a nanosecond. Well, just like a dragster or something like that. So there are always examples of optical computing, and they are always so far they've always been very inefficient. Perhaps an exception of that will be quantum optical computing. We'll see. I was going to talk money though. Forward error correction is a type of coding that corrects that resends a few bits, and it resends it in a very complicated algorithm. And so on the back end, you don't know what your pulse train is because you are sending information, but you know that a certain number of bits are very strategically resent. And so you can go and you can compare a bit to one where it was supposed to be. And if those are right, then you know you don't have to do correction. If they were wrong, then you know you have to do some sort of correction, and the algorithm tells you which way you can correct it. These are very complicated algorithms called forward error correction, and they give you 8 dB of gain. That's doubling, almost 3 doubles, which means you go twice as far, 3 times as far. At 10 gigabits per second, a forward error correction chipset, a special ASIC that was designed by, let's say $10 million, $20 million, some number like that in a year or so. Those were sold for $800, a chipset. So every laser and every receiver had an $800 pair of silicon logic.
For what?
It's called forward error correction, and it's an example of coding in a transmission line.
I mean, you said that every laser in which system? Though?
Oh, in a 10 gigabit per second optical link between, say, 2 cities.
Wow.
Okay. I'll talk about that towards the end of the class, OC192. It turns out right now, let's say 80% of the build out there runs at OC192 or 10 gigabit per second. Okay? People are starting to work on FEC at 400. Every time you go up by a factor of 4 in telecom, the rule of thumb is that you can charge 2.5 times for that. So every generation, you go up by a factor of 4, and your cost point goes up only by a factor of 2.5. And everybody wins. The vendors win because they can do things more. They're forced to. They can get a premium for their development. The vendors win. The people who buy them win because they get to have more bandwidth for less per cost. So if you do 10 gigabits per second at $800, a factor of 4 gets you up to 40. That's 2.5 times. And then another factor of 10, what does that work out to be? About $20,000? So by that rule, a FEC chipset that runs at 10 gigabits per second to 400 gigabits per second is now $20,000 about. It's an expensive piece of silicon germanium, actually. Okay? Just I'm digressing. I apologize. Okay, so ADSL is kind of an example of that. Small transmission bandwidth. RZ kind of violates that a little bit, but it turns out that it gives you benefits that outweigh that. Turns out a lot of impairments scale with bandwidth. That was our argument for single sideband in QAM. Chop the bandwidth in half, and you don't have as much dispersion, and even some of the nonlinearities swing your way as well. So keeping your transmission bandwidth down is always a good thing. We talked a little bit about error detection. One example of that error detection we did when we were looking at the gray codes. The zeros represented negative values. The ones represented positive values. If you're going to have bipolar, you'll have an even amount of zeros and ones, and so you can just count those. And if your statistics are off, you know you've made some mistakes. To these FECs, where use something like a Reed-Solomon or turbo codes to calculate an overhead, to resend some bits very, very strategically, typically 8% or 20%, somewhere in that range of your bits, and you can do a lot more detection. Okay. Last one, and we're going to debate this a little bit. Transparency, so that any kind of data is treated the same. So video, voice, audio, all those, spreadsheets, whatever was behind the ones and the zeros should all be treated the same by the coding. True or false? Is that always true?
You mean they're saying like whether telecom or like ISPs will treat data the same? Will they don't? I mean.
So you're okay. So your comment is that not all data is the same when it comes down to the use. It comes down to the internet connections that you use. But should it be the same? Should it all be the same?
I mean, should people treat it the same, or
should your coding scheme and your transceiver and your receiver be transparent to the type of data that goes through it? The answer is probably. The answer is probably. That's why it's a desirable. It's on this list of desirable properties of codes. But on the other hand, I can imagine if the internet migrates to 80% video, and you can come up with a coding scheme that's highly advantageous for video, but not as good at voice, then the inclination might be to go for it because you're making 80% of your traffic much easier to handle. Okay, just a thought. Okay, I don't want you to think that that's cast in stone. All right, I'm going to give me just a sec. I want to. Review some of this stuff with some fancy charts and there we go. This is how I am still here. That's always good. Okay. So okay. The same set of slides from my webpage as this. Here's some thoughts on line codes. It goes back to punch tape. Paper tape. Has anyone ever thought about that? Like not just punched cards, but just a thin piece of paper that with holes cut into it. That's how I used to save my computer programs written in BASIC in the 1970s, when I was half your age. So, and in fact, that coding structure dates, that storage outlet structure dates way back. If you think about textiles, you wanted to weave a sweater. Your pattern, for example, in your sweater. In the old days, what they would do is they'd have the yarn, the dark yarn and the light yarn, and they would take different paths through pegs on a board, so that your diamond shapes and your other patterns would come out at exactly the right spot. So programming a mill amounted to punching or putting pegs in and routing your yarn around it. So that's sort of a precursor to the computer use of it. Those were read by a little stylus, a little metal stylus that would rub its way along the paper, and when it would see a hole, it would flip up and down. The problem with that is it would wear out your program, because the stylus would chip away at the edge of your little hole. And so when Bob Beard, have you ever met Bob Beard or listened to him talk? You should please invite him to give us a talk to the IEEE student section. He's the inventor of record of the LED at Texas Instruments back in the 60s. Absolute one of the brightest people I've ever met. And he went to patent his LED that worked in the near infrared, revolutionary, gallium arsenide structure, 3-5 structure. Spends an hour with the patent lawyer describing it, and the patent lawyer summarizes it by, let me get this straight, you invented a light bulb that nobody can see. So they put a part number on it, and they made it, and they started to sell it, and they did, and people bought it, which surprised the heck out of them. And they went to visit the customer, which at the time was IBM, and they said, why are you buying our part? How all good market research goes. And they said, well, the styluses that, we don't want to use styluses because it rips the edge of our punch cards and punch tape. And so what we've decided is to use your LED and a detector, and then we can read the on and off, on and off, on and off, and not harm the structure. Okay? Digression. So this guy here is an example. That punch tape is an example of unipolar NRZ. Okay? And then here's polar NRZ. And notice over here you have the bandwidth. And so you can take some time to think, to look carefully at where the nulls are and how much energy would be filtered out here versus here. And later on we'll get an idea of what will happen to our decision-making capability if we got rid of that versus that, if we lost that much power. Would that materially affect the number of ones we got correct and the number of zeros we got correct? Okay. Unipolar RZ, much broader spread of bandwidth. Bipolar RZ, you can now see the loss of the DC component if you compare here to here. And then here's the Manchester coding. And again, what I would encourage you is here's a 1 1 0 1 0 0 1. You can see the upward edges, and you can see where the edges are versus how often you have other rises and falls. Okay? You were asking about that, so I wanted to just point that out to you. Okay, now, to segue into the next section of the course that I want to talk about, we're getting into noise. We're getting into what happens with noise in our systems. And so I'm going to gradually go from this digital world into an analog noise. But this is a good way to start. What we have here is something called an eye diagram. Kind of weird. I didn't realize I had to do that. And so what you can think about here is there is a transition from a 0 to a 1 and back down to a 0. Okay. Here's 0, 0, 0 being sent. Here is a 1, 1, 1 being sent. And kind of out of colors. Here's a 1 to a 0 to a 1 being sent. This top piece, this top trace, would happen right out of my transmitter. So what I would do is I'd make a nice transmitter, and I'd send a random set of 1s and 0s, and I would re-trigger at the beginning of every time slot, or at the middle of every time slot. And I would just let this run so that there'd be 1 million of these transitions. And every one of those million would line up right on top of each other, right out of the transmitter. Okay? So I'd have a very, very, very thin curve for each one of these guys. Okay? And we call that an eye diagram. I guess because, well, I'll use blue eyes. You can imagine a little eye in there and eyebrows on it. This is so much fun. I'm having a blast with this. But you can see that this term of art is called an eye diagram. Now, you go through a channel, and the channel beats the heck out of this pulse train. And all kinds of bad things happen. Okay? For example, your 1 gets attenuated. And sometimes it gets attenuated a lot, and sometimes it gets attenuated very little. But regardless, you have a spread of values a spread of levels, a spread of values that are all equal to a 1. So all of those are a 1, but analog way, you might have 0.7 volts and you might have 1 volt, and a whole bunch of samples in between. Okay. You would think that you would always be dark at the bottom, but the light or the energy has to go somewhere, and so sometimes it'll leak into from the high spots to the low spots. So some of the light that was here could get delayed and fill in where it should be dark, the time periods that it should be dark. And so as a consequence, my 0 level is also going to be spread. I'll have sometimes where I'll have a very low level, and other times where I'll have a fair amount of pollution, a fair amount of energy in the dark spaces between 1s. Okay? If this were bipolar, I wouldn't even have to fabricate that. The negative A over 2 would just have some variation on it. But I want you to realize that it happens for unipolar as well. Okay? You can think about it this way. You've got a signal, a wireless one, and it bounces off a couple of buildings, and it arrives at the receiving antenna many nanoseconds later, or many microseconds, or a few microseconds later. You don't know if that's going to be a 1 or a 0 where that energy falls in, and if it's a 0, well, the 0 now is some floor. Okay? So that's loss and scattering. You also have jitter. Some pulses, some transitions happen earlier or later, and some transitions happen earlier. Those are transitions, falling transitions, similarly rising transitions here. Some are going to happen earlier, and some are going to happen later. So these are jitter. Okay. In any case, whether I'm addressing the height of the ones and the zeros, or I'm jittering around it, this eye is closed relative to the first eye. That's another term of art. So noise, both in the amplitude and in the timing, will work to close the eye in your eye diagram. Okay. So, what does this mean? We're going to do this more carefully next time, or maybe start this time. But if I've got to decide on this guy what is a 1 and what is a 0, it's pretty easy. There's my 1, and there's my 0. I could probably set my threshold right down the axis there. And if at a specific time, if I'm above that, it's a 1. If I'm below that, it's a 0. This eye is still pretty good. That eye is still pretty good. There's a lot of opening or white space between this hash of zeros and this hash of ones. So again, I can draw my line and make my decision. That's going to be a 1. That's going to be a 0. There's a lot of daylight between there. That's not an economical system. If I've got an eye that's looking, even though this eye has deteriorated, there's still a lot of daylight there. So I can go farther. Or I can put more bandwidth on my line. And so what will happen eventually is I'm going to keep deteriorating these ones, and my where I put my threshold is going to get harder and harder and harder to figure out. And that's good engineering. I want to go as far as I can, or I want to pack as much data as I can onto this line, and still be able to reliably, to some measure of performance, decide whether I'm sending a 1 or a 0. Or, I'm sorry, decide whether I'm receiving a 1 or a 0. Given that a 1 or a 0 was sent. Okay? Because this guy here, it's right on threshold, the transmitter knows it's a 0, but if it's right at threshold, I'm probably going to call that a 1. There's a chance I'll call that a 1. And so a 1 was received, and a 0 was sent, and that was an error at that bit. So now how many bits how many errors in that bit, what is the bit error rate that comes in that is acceptable, and is it acceptable or not? Okay. If I make a mistake and I have error correction, to some extent I can correct for that mistake. That's what we call. That's the purpose of forward error correction and error correction in general. So we're going to come back to that problem, and we're going to look very, very carefully at that thresholding. The idea is exactly where do I adjust this threshold? Exactly where do I put that threshold to minimize the false readings, to minimize my bit error rate? Okay, that's one of the lectures that I'm going to give. Now let me just see where I am on this. Yeah, okay. Here's a close-up of the same information. Okay, here's a close-up of the same information. The noise or the distortion level is labeled here. That's what we had before, and then similarly down below as well. And then the time variation of the zero crossing, I call that jitter. But again, both of these close the eye. Close the eye from the top and the bottom. Close the eye from the side to side. This is interesting. What we want to do is we want to look at the signal-to-noise ratio. In fact, one of the things, the job of what we're going to do in the next lecture, maybe beginning today, is to figure out a formula for that signal-to-noise ratio. And in this graph, they're just saying, hey, in the middle, you have the most daylight, the most separation between a 0 and a 1, and so that's a good place to be making the decision. Another reason why clock recovery, timing circuitry, is so important, so that you can slot yourself in to where you want to be. Now, one of the things I want to point out with this graph, and I'll come back to it later on, but I want to point out with this graph is, if I draw a cross-section there, then I have samples. This looks kind of thick in here, so there's more samples. There's 1 point there, there's 2 points there, there's a whole bunch of points in here, and then there's nothing out there. If I turn the height of these, what I have is I have voltage and I have number. So let me turn that on its side. I have number as a function of the specific voltage level that I receive. And that pattern, what do you call that? Well, if I'm just adding up the number of voltages in any given bin, what's that called? Is it a histogram? This is a histogram, right? This is the number of people at this voltage. This is the number of readings at this voltage. This is the number of readings at this voltage. And so if I plotted this, I'd have a histogram. And if I had enough of it in a normal process, a random process, a Markovian process, I would indeed get a bell curve. I would indeed get a specific type of distribution. Okay? So you're right. This in fact could be one way to approximate that. That could in fact be a histogram. I'm sorry, a histogram that could lead to a bell curve or a Gaussian distribution, a normal distribution. Gosh, what course am I going into now? 3341. Yes. So this is exactly, this is a lot of the things, now that is a prerequisite for this course, right? Well, now we're beginning to see why. So we have stochastic processes that lead to distributions of data. And if this is my ones, and I have another histogram down here for my zeros, I can imagine a distribution for ones, and I can imagine a distribution for zeros. And take a look, they overlap. And so if I'm in that region, there's a good chance that I'll call a 0 a 1, or a 1 a 0. Both of those would be mistakes. So what I need to do is I need to figure out exactly where to put my threshold. Exactly where to put my threshold in order to minimize those mistakes. Okay? So, from an experimental perspective, or from a design perspective, I could assume that I have a distribution like a normal distribution. I can assume that, and I can do my design around that. Okay? The other thing I could do is I could keep a record of of all the different voltages that come in, and know what my distributions are. Okay? And design around that. Okay? In either case, and this I'm going to remind you about distributions, in either case, what I'm interested in, well, let me draw it again. Over here. A distribution that's either a normal curve or empirically determined. I'm going to have a centroid. Another word for that is an average for that distribution. And I'm also going to have a spread of that distribution. And another word for that is a moment, or the standard deviation. Okay? And so those two numbers, well, the average and the standard deviation, the average and the standard deviation for the zeros, that's what's going to go in to our signal-to-noise ratio. Okay? Some math between here and there. But what I love about it is all the stuff that you're going to hate, conditional probability reminding you of that from probability and statistics, where you'll look at it, you'll say, I remember being told that. So we have to slug all the way through that. And then I promise you, at the very end, we're going to get a really beautiful formula that's really intuitive and really lovely. One that you will probably remember forever and use it in just a trillion different situations. Okay? That's called building up the expectations. And trying to get you back for Monday. All right. Now, oh good, I've got plenty of time to digress. I really like that. These are actual eye diagrams for two optical systems. One is at, what am I doing? There we go. One is at OC 192, which in English means 10 gigabits per second. Which means 10 gigabits per second. Which means every 100 picoseconds, a 1 or a 0 comes through my detector. And as I said before, the majority of the links in the ground now, in the glass now, is at 10 gigabits per second. Which means it's at the end of its life cycle. It's been fully deployed. It's fully used. It's at the end of its life cycle. And 40 gigabits per second is coming up, and 100 gigabits per second is also coming up in certain applications, certain areas. Okay? This is an old chart because this is OC48. If I take 192 and I divide by 48, I get 2.5. And so this is at 10 gigabits, 10 gigabit per second, and this is at 2.5 gigabit per second. Yes, sir?
What does the OC stand for?
Oh gosh, it is a. Oh, it's a good question. Actually, it's a standards question. It builds from it builds up from the very basic STM data light. It just keeps going. I have a feeling the O stands for optical, and I'll guess that C is a circuit. So optical circuit, yeah. Do you know?
Optical carrier.
Optical carrier. Okay. So optical carrier of 2.5 gigabits of 48 times the base level for I think DS1 or something like that. Okay. Telecom standards. Telecom standards controlled by Telcordia in the States and the ITU globally. Question.
Any reasoning for the 192 or 48?
Yes, it's 48 times the base level for digital communications. So when digital communications came into play, they went to a certain fast speed at the time. Over time, you had factors of 4 improvement every generation at 2.5 times the cost, which is why 48 is easily divided by 4. So you went from 1 to 4 to 16 and so on. Okay? So that's the progression up to this guy here. But what I want to show you also so do you see they've labeled the decision region, okay? And this guy here, this little polygon, is called a mask. Okay? If your transceiver violates that mask right out of the, not at the end of the channel, but at the start of the channel, right out of the transmitter, you don't meet spec. And so this transceiver rises up like this, falls like this, and rises like that. So all the parasitics, all the inductors, all the capacitors in that RF circuit are designed to make this transition avoid the red lines, the mask, to stay out of the mask. If you're switching something so fast, it's pretty likely that you're going to have some wiggles on it. These transitions are marvelously smooth. They have been very well executed, very well engineered. There was a company that was transitioning from here to here, and on their rise, they had a little wiggle. And the trail end of that wiggle, every once in a while, violated the mask. It took them 2 spins, 9 months of spin, to iron out that wiggle enough to get above the mask. In that 18 months, you had a team of 20 engineers, a company of about 40 people, not shipping product for that 18 months. So do a rough number. 40 times 100K plus toys. 40 times 200K. 40 times a million. That's their burn rate that they went through for 18 months. 1.5 times those numbers of not shipping product while other people were capturing percentages of the product, of the market, that they would have to win back. Okay? That drama happens every time you switch from one clock speed to another clock speed. Okay? Do you remember the graph I showed you at the very first day of the class? 3 orders of magnitude in bandwidth every 50 years. My friend says that's a low estimate of the pace right now. So that's the opportunity. If you've got really, really good engineers, you are a really good engineer, and you don't have that wiggle, and you get to market 18 months ahead of your competitors who do have that wiggle, you are saving your company. Trick is, you can't do that once. You have to do that every cycle, every design cycle. What have you done for us lately? That's engineering. Sorry. Yes, sir.
No, I was just looking at it this way. I didn't notice it before when you had the cleaner eye diagram.
Yeah. Well, the other ones were abstract. This is real data.
Right. So the noise and the time variation are just where on those masks they approach.
So, okay, let me be clear. This data is right out of the transmitter. Okay? This data is right out of the transmitter, so it's very clean. So this data is right out of the transmitter, and this one is at the receiver. Okay? And so the channel has done all this stuff. The channel has done that stuff. Your circuitry works again and again and again to give you this nice thin line. If you have jitter on your circuit, you're in a world of hurt. So this is back to back. They call it back to back, right out of the transmitter. And then some clown has put in a transmission line, like between two cities, to actually carry data. Okay. And so what we're seeing here, this is just an abstraction. What we're seeing here is a back-to-back test, so those lines are very, very, very clean. And when I'm talking about a wiggle on them, I'm talking about a consistent ringing in the RF circuitry that gets you in trouble. Okay? And you can imagine needing that. Have you taken control systems, say with Nick Gans? No? So some of you have taken control systems, linear systems? So you remember you talk about stiffness, you talk about Q. You can move things really fast if you've got high Q. On the other hand, you're more likely to oscillate. And so that's what's going on. That's the trade-off going on here. Okay. This is all ones and zeros. 0 and 1. Bipolar. I'm sorry, not bipolar. Just on-off keying. On-off keying. This is a 4-level system. So you can have eye diagrams for 4-level systems. And you can go from a 0, let's say 0, 1, 2, 3 levels, 4 levels. You can transition from a 0 to a 1, a 0 to a 2, a 0 to a 3. You can stay at 1. You can go from a 2 down to a 0. All those possibilities. And so now you have a mask that goes there, a mask that goes there, a mask that goes there, and there. You have eye diagrams for higher levels of signals. Okay. This is more common in RF than it is in optics, but optics is moving there. You can see that you're